Yeah, my name is Klaus Gottschalk. I've been here to the HPC Advisory Council several times. And actually last year, as part of Lenovo, I moved to Lenovo as part of the x86 transaction with Lenovo. And I'm back at IBM supporting HPC since August last year. So power is actually my background, so I'm coming home to power in a sense. What I'd like to show you today is that we never moved out of HPC. Even though we decided to sell the x86 department to Lenovo, it was never our intention to move out of HPC. So power is the platform we are bringing back. We had power for HPC since years, and actually our Blue Gene systems are part of the power brand as well and very visible on the top 500 list still. But we also decided to bring a new platform. It's based on OpenPOWER. We already had a presentation on OpenPOWER. I don't want to repeat that, but I'd like to show you what we will build as an ecosystem around OpenPOWER to enable high-performance computing with power again. And also, I'd like to show you what we already did, what we decided to do with the CORAL projects, the two projects we won together with our partners in the OpenPOWER community. I brought you a lot of slides. I might skip over them, so they are just for your handouts then. First thing I like to share, observations, and maybe most of you saw this observation. It's actually something you can easily derive from the top 500 list itself. So currently, the innovation around HPC is slowing down a bit. We see that the performance we are getting, even though that the applications are ready for scaling to the largest systems, the application performance we are getting is not that good anymore. So one of the things is to address these points, to bring innovation back into HPC. And also we see that a lot of other things are happening. So scale out and hyperscale in data centers is really changing something in the market. Also, we see that cloud computing is catching interest in the HPC market. Requests are coming in how we can make use of public clouds also for high-performance computing, how we can incorporate into such a technology into a classical HPC. And of course, open solutions is something which is also always happening. So from that observation, we actually see some first insights coming out. So during the past years, we applied high-performance computing technology like we always did, like we did the 10, 20 years in the past. But nowadays, because of that, we see a lot of data in infrastructure silos. So moving the data is a very common problem in high-performance computing nowadays. And a lot of people just build their HPC workflows around the data movements they use. And from that, we see that the workflows are even getting more complex and getting into the center of interest of us and others to optimize them. So workflows, optimizing a workflow does bring even more performance than just optimizing the computing, because the computing, the high-performance computing part in a workflow might be only a small fraction of it. But optimizing the whole workflow is really something which can improve the application performance. We also see that a lot of centers are just adding capacity and run out of power, run out of cooling. So all these things must be taken into account. And data duplication is again a theme for moving data again. So what is our strategy to move into the HPC market with power again. And one of the most important thing we immediately realized, the innovation which we are looking for is not coming from IBM alone. It's a community effort, and therefore, one of the first things we did, we funded the OpenPOWER Foundation to generate over the next couple of years an ecosystem which really enables innovation back into high-performance computing and probably enable to come back to Moore's law on the application performance and not only on LINPACK. So we hope that we can do some innovation ourselves. We also see acceleration as a really important topic because we all know that the clock speeds of the CPU, even though the power processor is clocked very high, we don't think that the clock rate will go up very much during the next years. So in the end, we see us doing some things, but also around the high performance, about the OpenPOWER Foundation, we see a lot of other things happening. And also acceleration we expect we could do together with our partners. And enabling the acceleration in power is one of the key parts of our strategy. So our vision out of that, from the observation I just made about data movement, about data-centric computing, we think that putting the data into the center of the workflow is the most important thing. Minimizing the data movement and allowing access to data from high-performance computing, from pre- and post-processing. So data storage, and in that sense also our spectrum scale product, the GPFS, is important in that area. And also enabling computing anywhere, everywhere. So cloud computing incorporated into the high-performance computing technology you probably install in your data center is something we think about it, and we actually enable already in some of our customer installations. And everything must be, in the end, application-driven. You see, we are not interested in doing very high LINPACK numbers. Of course we could do, especially with acceleration, we could do very high LINPACK numbers. But interesting you and your users in the end is application performance. And I think that's what we should concentrate on. So maybe we need a new metric on the LINPACK, on the top 500 list. But maybe we keep LINPACK, but also keep in mind that the application-driven design is really important. These are our commitments, actually, where we decided to bring in innovation ourselves. Of course, as I already said, the OpenPOWER Foundation, all the members, all our partners in the OpenPOWER Foundation, and a lot of them are here at the conference, they are also part of that strategy. But we decided to bring in, on one hand, a new processor design. Currently we are running Power 8, so there will be a new Power 9, which incorporates a lot of technology for acceleration, which enables acceleration for high-performance computing. We did already some of them with the CAPI interface, and we will include the NVIDIA link later this year to enable communication between the GPU and the main processor, so using then the GPU more like a co-processor in the total solution. As I already mentioned, file systems, since we are talking about data-centric computing, is also important for us, and I have some examples on the end of my slides where I show some examples. And then, of course, software is important. Yes, we are doing with power hardware sales, but the ecosystem also consists of software, and we expect that acceleration will become a lot more easier with everything we and our partners do in that area. So enabling all the parallel environment and enabling our ESSL is already done for GPU computing. But we are also providing technology for LLVM, for instance, for OpenMP4, and we think that in that ecosystem, acceleration will be for a lot of applications just incorporating some instructions for the compiler to offload some of the workload. With that, we already talked about these technology changes to our clients since some time. With that, we already had some important wins for us, which shows that the technology we like to provide in that area is also accepted by customers. The most recent one is STFC in the UK. It's the Scientific Council, so that will be one of the power installations. We also have in the area of data-centric computing a very good reference with DESI, which is the particle accelerator near Hamburg, which does a lot of data movement, and we were able to accelerate these data movements by just incorporating everything into centralized storage. So the data movement actually went away to a lot of extent. But we also had these very important wins for us out of the CORAL project. So IBM, together with Mellanox and NVIDIA, as part of the OpenPOWER consortium, we were able to win 2 out of the 3 CORAL bids. So to me, that means it looks like that our offering for CORAL was even more convincing than other offerings on the market. And our offering consisted of accelerated computing based on Power 8 and also Power 9. Later this year, as I said, we will bring out a first system which will be installed at the site as a porting system, and then in 2017 we will do a major installation in both of these sites. And for me, this is also generating a lot of push into the direction of accelerated computing, because a lot of applications which are running on these sites will be, during the process of installing the systems and preparing for this project, will be moved to an acceleration possibility. So will be enabled for GPU acceleration and not only for GPU acceleration. It's also very important to note that even though that the GPU is very important in our strategy, we think that acceleration is important in nearly every step of the workflow. So we will also put acceleration at the networking level together with Mellanox. We will also put acceleration at the storage level, providing a CAR-P interface-enabled card, which makes it very possible to reduce latency in file system access very much. And for me, this is really showing that our strategy was convincing to these customers. So OpenPOWER was the foundation of that, was actually the starting point of the environment which we need for that. And in the end, we provided something, some technology, some intellectual property of IBM to start that. But as I said, we were sure that this will pay off. This will generate something which brings innovation back into HPC. What we did is we actually licensed our processor intellectual property such that every partner in the OpenPOWER Foundation can actually take it and build his own processor out of that. And some first things are appearing on the market. In China, a company is building a power processor based on our specs, based on our intellectual property, which is not sold by IBM. It's a Chinese power processor. Of course, the power is based on building blocks. They replaced some of it by their own technology and decided for other things. So maybe the number of floating point units is different, the number of integer units is different, but still it's a power-based architecture and being binary compatible to all power systems we ever built. So that's the possibility to get a power-based system from then. And also the Tian company decided to build boards based on our processor, and which can be bought directly from them. And actually one of our systems is an OEM product from Tian based on the very same board. We also decided to put in, to open up a lot of the interfaces for our partners to plug into that, and also bring interfaces from partners into the processor, for instance, the NV-Link. So opening up the CAPI interface and bringing technology in that enables acceleration on the various levels. And last but not least, the systems and the software itself is also very important on that one. And we really enabled and shared all the development needed to build an HPC system around of that. And as you probably already saw, besides the Coral leaderships, I already mentioned Oak Ridge and Lawrence Livermore and their goal of being able to push the application performance, possibly not the peak performance, but certainly the application performance at least 5 times or 10 times higher than today. But we also had other partners joining into that. And if you look to that chart, you also see that in our view, cognitive computing, besides the data-centric approach, will play a role here. So some of these centers also decided to become partners of ours in the machine learning or cognitive computing part. And also very important in my view that we opened already in 2015 some of the parallel acceleration and design centers, and most prominently in Europe, it's the Jülich Research Center, which is a partner of ours, and enables their applications to run on the ecosystem created around OpenPOWER. I cannot avoid this chart just showing you how the OpenPOWER Foundation is growing. So we are just over 190 members already and getting a lot of interest in that. You see, I spent most of my time the past months just talking about OpenPOWER because the interest in our technology, the interest in the technology of our partners is growing so fast. And from that ecosystem, a lot of applications are already then on Power now. Power means the Power hardware together with Linux. I'll show you in a moment that we decided to switch a little bit our hardware, to twist the hardware to enable the ecosystem which we intend to have, to make it even more open than that. And first of all, I'd like to mention the Power processor, and that's the current Power 8. And probably a lot of you know our Power technology, but since we are not so prominent with the Power server processor in the HPC market the past 2 years, I'd like to highlight some of the features. And most important in my view for high performance computing is besides that we can do a lot of flops per cycle, so the peak performance is there, but what I also like to highlight is that the memory bandwidth was always a design criteria for the Power processor. So this Power 8 chip in the current version has 8 memory channels, and they're bringing together 230 gigabytes per second of memory bandwidth. Of course, how many of these channels are actually attached in a board depends on what packaging we are looking for. But if you have a memory-intensive application, if you have applications which depend on data and movement of data, then certainly we have the right choice in the Power family to enable that. So fast cores, we have 8 threads per core, enabling them also for simultaneous multi-threading. And also, if you remember, Power was also very well known that enabling simultaneous multi-threading on a power system, which will bring a higher throughput to your application. So using simultaneous multi-threading, using SMT on Power actually brings you more throughput. So that's a difference to other implementations in that area. Usually on a high-performance system, we enable at least 2 threads per core. And the logical threads then bring you the throughput you're looking for. And especially for the systems we design as OpenPOWER branded for the high-performance computing stack, we also enable them for large memory, so at least 1 terabyte we support in these systems. And these are some measurements we did in the past months, doing the high-performance applications, the most common ones, which we see in our customer sites. And you see, in most of the applications, we are doing quite well. Of course, there are applications which are optimized for AVX only, which I don't consider portable anymore. But all the others, they are easily ported. And in an application study we did together with one of our customers, we received a comment from the customer that he was able to generate an executable for the Power architecture within a day in most of the times. And even though we didn't optimize, we outperformed an Intel Haswell system with the same core count in that comparison. And on some of the applications which really depend on memory bandwidth, we are a lot faster. So twice as fast as an Intel CPU. And that also keeping in mind that probably the size of our vector unit is not the same size of the Intel Haswell. So in my view, the vector unit size is probably a little bit overgrown in recent processors because the applications cannot make use of it. But memory bandwidth is important, and that's what I like to show you on that chart. The next thing I'd like to go a little bit into is the acceleration things I already mentioned. 2 of the acceleration technologies which we will enable for the Coral installations is the CAPI interface, the Coherent Accelerator Processor interface, which is enabling a low latency protocol on the PCI bus. So a card which is CAPI enabled can bypass most of the software stack which is necessary for PCI bus communication. So an FPGA plugging into that CAPI interface has a logical shared memory with the main memory of the node and can access that memory at a very low latency. Also, any card which is a storage card, for instance, a SAS card, plugging into that and also enabled for CAPI reduces the latency for flash-attached memory, for instance, such that big memory applications, an in-memory database, for instance, can really perform 3 or 4 times faster compared to an Haswell CPU on that side. The other technology bringing the NVLink into the power processor is something we will see this year. We will bring out the second version of Power 8 in the mid of this year, and with that we will bring the NVLink, the NVIDIA network link, which is nowadays only available between GPUs, into the Power 8 processor. And by that we are bringing 3 times higher bandwidth to move data between the GPU and the main processor and also to the main processor interface. And CAPI is really a game changer for accelerated performance. our expectation and the expectation of NVIDIA that an application running shared on the Power 8 and the GPU will probably run about 30% faster than a comparable system just using the PCI bus for accessing the GPU. So that's a real way to bring performance to the front. And with this slide, I'd like to show you some of the roadmap which we actually developed for CORAL, and a roadmap which any of your sites can also participate with. The first node, which is mentioned on 2015 on this side, is actually available. This system is a 2-socket system which can hold up to 2K80 GPUs. So in my view, NVLink is still not there, but the CAPI interface there, that's an application porting system which enables for acceleration. That's available since November last year. In 2016, in about third quarter, we will bring out the new Power 8 Plus processor, which includes the NVLink for the first time. And with that, we can bring up to 4 Pascal GPUs into the system, and it's no longer plugged into a PCI bus. It's actually a co-processor in the system, sharing logically the address space of the processor also with the GPU. So accessing memory from the GPU is just a logical movement behind the scenes of the data, or also vice versa. If the main processor, if the Power 8 processor needs to access data which is stored on the GPU, it's just part of his address range and he can just access it. So that's the way where we think that enablement of the acceleration is then taking place. So that's where we and NVIDIA together think that 30% more performance you will get out of the GPUs in such system. And then finally on the right slide, and finally doesn't mean at the end of power. Of course, there is a power development is ongoing, but that's the system we will deliver for CORAL actually. It's a new processor architecture, so it's a new major step for power. It's the Power 9 processor, different numbers of cores, possibly a new clock rate, and also enhancements on the CAPI and the NVLink interface. So the NVLink will be even more tightly integrated into the system. And the integration will be that tight that the memory space of the GPU and the memory space of the main system will be cache coherent. So at that stage, the GPU is actually a coprocessor. It's no longer a logical shared address space, it's a physical shared address space. And we think that a lot of applications will then perform very well on this system. And we will actually also increase the number of GPUs which will be supported on that system. But as we did in the past, these, especially if they have a larger number of GPUs, you can imagine the energy density is very high. So that system will be water-cooled in most of the installations. And that's also spanning some of the things I was doing here at the HPC Advisory Council during the past years. Because we were the ones enabling also water cooling for Leibniz Supercomputing Center and bringing the advantages on the energy efficiency on that system. And we will redo that also on the 2016 and 17 system. Water cooling will be an option for the high density of GPUs. It will be necessary, but for all the other systems, it will be an option. And we will also, of course, enable hot water, direct water cooling, as we did for x86 in the past. Yeah, we already had some systems, and the only thing I'd like to explain you here is that we branded these systems with an LC at the end, which really demonstrates that these are open power-based systems and they are running in little Indian mode. So Linux on Power is nowadays no longer a big Indian operating system. Power always was able to switch the byte order. So the Power processor with one pin could always switch the byte order. And usually this is a boot parameter for the operating system. Of course, AIX and other operating systems which run on Power nowadays for commercial applications will stay big Indian operating systems. But for the high-performance computing market, we decided to be in the byte order also compatible to most of the installations nowadays. So porting an HPC application to Linux on Power is more or less a recompile, because the byte order is the same, the environment is the same, it's the Red Hat operating system, it will be also SUSE less in the future, and we also support Ubuntu currently as the operating systems. And these LC systems, they cannot switch. They are not ready for AIX. There are other power systems which are ready for AIX. The LC systems, because they are designed to be an open power HPC solution, then can we also sell in a different price range. So we will meet our competition here in the same price range as you would expect for other HPC solutions. I already mentioned that we are looking at data-centric computing. And data-centric computing, we also see very important that software-defined infrastructure is there. And we will optimize everything in that range, and we will optimize the workflow for that. So high-performance computing, analytics, big data, we all see part of the same, which we will put on this IBM platform for computing with a total environment which supports data-centric computation on that one. And as you know, LSF is the scheduler of our choice, but not the only one, of course. But with LSF, we can also support high throughputs, and that's an example here I'd like to show you and leave you in the handouts. Because this client really had a big advantage from using LSF as part of the software stack. We are not bound to LSF, but if you like to use LSF, it will bring you a lot of advantage in the throughput. And as I mentioned at the beginning, data-centric is in our thinking centered around a central data storage where all the systems can access the same data. And we will provide the spectrum scale, the GPFS solution for that. And also, one of the references on that one, which I mentioned in the beginning, is the DAISY Research Institute in Germany, the particle accelerator in Hamburg, which reduced the amount of data they need to move from the experiment site to the pre- and post-processing, and also the computation was very much reduced because it's the same storage which they provide even through firewalls directly to the experiment site. And last but not least, I like to reinforce that in our view, the intention is to also provide fast workflows in the end. So not only a fast computation, but the whole workflow. And we see for all these memory-intensive applications, flash memory as a very important solution in that area. And flash memory using the acceleration of copy attachment is really a key thing in that area. Yeah, and with that, I'd like to just finalize my presentation by highlighting that in our view, the application performance, the application you see in the end, the total time for the workflow in oil and gas, the total time for the workflow in bioscience, the total time for a workflow in technical computing is what's important. And we try to look at it as the full picture. So enabling the new workload, maximizing the performance and not only the compute performance. And also having an eye on optimizing the efficiency is what we like to bring together with the OpenPOWER Foundation to high-performance computing. With that, I'm through. I just have some more information and I'm ready for some questions. And a final remark, International Supercomputing Conference in summer, we will directly before that have an OpenPOWER Summit, the 2 days before supercomputing. So if you're interested in OpenPOWER, just consider to come 1 or 2 days earlier to supercomputing to Frankfurt, and there will be an OpenPOWER Summit meeting. And with that, I close. Thank you very much.